But there are problems with the process, and they're mainly due to the fact that things are so disjointed. There's designers that are throwing CAD over the fence to the analysts.
Exactly.
And there's researchers in the back room that are fretting about manufacturing parameters and compliance. So what if we could connect design, manufacturing materials, and put science front and center in the tool chain?
Now we want to start to control the shape. If we were using traditional manufacturing, such as milled parts or casting, we'd want to define things like our draw direction. In this case, since we're doing additive manufacturing, we're just going to simply specify some symmetry constraints, and then we're going to allow this to take on a more organic structure, which will be a better performing design. As I further post-process these results, what I'm able to actually see virtually in real time, I can see the target mass, so I can understand what's the mass going to be, what's the total volume going to be, and then I move forward, and with a push of a button, I generate a shape. Now this is really, really important. This is my favorite part of the workflow, because working with traditional tools on the market today, this is the nightmare. This is the over-the-wall part where we can never move and have an actual workable design.
So in our new approach, we are sharing the same model between simulation and optimization. What we created at the end of the optimization process is now available for the designer to go through the detailed design phase. The designer can further refine the part using organic modeling tools that are focused on the design intents. As a designer, you can explore and generate more organic shapes on target using the power of additive manufacturing and benefit from traditional manufacturing processes.
The idea is that can we take information from the lower scales, from atomistic type simulations and from phase field simulation as shown here on the lower part of the graph here, leverage that into calibrating continuum models as shown by the equations in the center, such that they can be used effectively at continuum scale, finite element scale, at part level type simulations. So traversing again to summarize the whole slide here, from 10 to the minus 9 to 10 to the minus 1 and larger scales in meters, the idea is that we can hopscotch all the scales as to build calibrated model for part level. You obtain contour plots like this of temperature gradients as the part is being printed. So now, basically you have the laser inputting heat into the system, and you have the cooling and convection and radiation that happens continuously and compete with each other, leading to this rapid thermal gradients. In the end, what you get is a deform plot or distortion plot as shown here, and you can see that even with this simple application that we did here, we get about 0.5 millimeter distortion, max distortion in the part.
And we've done it in a way that's open and customizable, because we realize that together with our community, we're going to have to, together, push the state of the art and the science of additive manufacturing. It's going to be a joint effort. This stuff is really new, it's cutting edge, and we're right out in front of it.